Alright, this is 6-4, the normal approximation of the binomial, part 1. In the later video, I'm actually going to use the calculator to go through the steps, so just bear with me. This one is just an explanation for what's going on. What we always have to remember when we're finding the z-score is, what are we doing the z-score of? In this case, we're doing a z-score for the binomial. So we need to remember the z-score is equal to x minus mu divided by sigma. As we saw in the last section when we did the central limit theorem and we're looking at samples, sigma changed because we had sigma sub x bar, we had mu sub x bar, which was the same as mu. So now what I'm going to do to match that vein of thought, this is different than the book, it's my own notation, so sorry. Our z value is going to equal x sub star minus mu sub b divided by sigma sub b. Now what I'm doing with the sub b is, it's for the binomial. Alright, now what we have to remember from the binomial is, what's the mean of the binomial? Oh, it's just NP. What's sigma? What's the standard deviation of the binomial? Oh, it's just the square root of NPQ. And if you don't remember what Q is the complement of P. In other words, Q is equal to 1 minus P. Remember this. Okay, so what does this do for us? It's going to do the same thing we did for the central limit theorem. Z equaling x sub star minus mu sub b divided by sigma sub b. Translating it for our binomial becomes z is equal to x sub star minus np, because that's the mean of a binomial, divided by square root of npq, which is the standard deviation of a binomial. And then what is this x star thing? Well, x star is either going to be replaced with x plus 0.5 or x minus 0.5, depending. And it depends if we include the bin. What do I mean by the bin? Alright, when you have a binomial, go back to your binomial, refresh yourself on the binomial. Alright, you have n number of trials. That's how many boxes you have that you're doing. The more n's you have, the closer our distribution is going to look to a normal. That's why we can approximate it. Look in the book if you want to understand that a little bit better. I just want to get through the nitty-gritty here. You also have an x value. You have a number of successes you're looking for. Sometimes you're looking for the probability it's greater than x. Sometimes you're looking for the probability it's less than x. Either way, you have an x value which is going to run through the center of one of the bins. Now that we're doing a continuous distribution, we're looking at area under the curve. You're looking at the area of this entire bin. Well, how do you get the area of the bin? Well, you have a start of it and you have a finish of it, and we're just going to run it through norm CDF on the calculator. So this bin has the same boundaries it had back in chapter 1, chapter 2, when we were doing all that graphing stuff. We always added a half or took away a half, and that's what we're doing here. So to get the entirety of this bin for this x, my x star is going to be both minus a half and plus a half. This is the only one that has both of those. And remember, this is going to be my start for my norm CDF and my finish for my norm CDF. This will make more sense when I do an example for it. Now, continuing this vein of thought for including or disincluding the bin. Alright, now, when we have the probability that x is less than whatever value we were looking at, alright, if I'm shading everything to the left, including the x value, then I have to include the entirety of the bin, which means I have to start my shading a little bit ahead of, or at the start of the bin on the right-hand side. So our x star would be x plus 0.5. Not to get confused if we're looking at the probability that we're strictly less than our value, which means I'm shading everything to the left of my bin, but I'm going to start at the edge of the end of my bin, which means it's going to be x star is going to be x minus 0.5. Sorry, let me fix that. X star is equal to x minus 0.5. Do you see that? Here's my bin, and I'm shading everything to the left of the bin. I don't include the x value. Which is different than when I'm looking for greater than. If I'm greater and I'm including the bin because I want the x value, When I do the shading, I have to shade through x, so I have to start at the beginning of the bin on the left-hand side. So it's going to be x minus 0.5. Similarly, if I'm doing greater than, which means shading to the right, I don't want to include x, so I add 0.5 to the bin. All right, this will make more sense as you practice it. But if you look at the table 6-2 in the book, it just gives the algebraic expressions. Here's the pictures that go along with it to explain what's going on. There's one more caveat I have to throw in there. When you're doing the normal approximation to the binomial, you must make sure that your mean n times p is never smaller than 5. Similarly, n times q, n times the complement, is also not smaller than 5. If this is the case, you cannot use the normal approximation. We cannot do these extremes. It falls apart. Got it? It falls apart when n times p is smaller than 5, and it falls apart when n times q is smaller than 5. Remember, if you got any questions, send me an email.